In this video, we'll be discussing isomorphisms of groups, and we will start with an example. I want to look at two groups. The first is Z sub 3 using the operation of plus sub 3. Z sub 3 has three elements, as we know, 0, 1, and 2, so those are the column headings and row headings of this table. And in the body of the table is the results of adding two elements of Z sub 3 using plus sub 3. The other group is the subgroup of S sub 3 generated by the cycle alpha of length 3 that I have written here. Alpha is the cycle 1, 2, 3. So remember, S sub 3 is the set of all permutations of the set whose elements are 1, 2, and 3. Since alpha is a cycle of length 3, we know that the subgroup generated by alpha has three elements. They are alpha to the 0, which is the identity, alpha to the first, which is alpha, and alpha squared. So I've used those names as the row headings and the column headings in this table. And then in the body of the table, I have calculated the products. So for example, alpha to the first multiplied by alpha to the second is alpha to the third. You add exponents. And since alpha has order 3, we know that alpha to the third is the identity, which in this table we're denoting by alpha to the 0. Alpha to the first times alpha to the first is alpha to the second, and so on. And one thing to notice about these two tables is that they are pretty much identical. If you eliminated the alphas in this table on the right and kept just the exponents, you would have exactly this table on the left. This is an example of two isomorphic groups. So here's the general idea. Two groups are isomorphic if their structures as groups are exactly the same. So we want to give a definition of isomorphic that will make this idea precise. The first step is to define what's known as an isomorphism. So an isomorphism is a function that shows that the structures of the two groups are exactly the same. So it's a one-to-one matching of the elements of the two groups, G1 and G2. In other words, it's a one-to-one function. I'm calling it psi from G1 on to G2, so that for all A and B in G1, if psi matches A with X and matches B with Y, then psi matches A star 1B with X star 2Y. So here's the idea in diagram form. We're thinking of the group G1 as being on the left here, G2 on the right, and psi matches A with X, psi matches B with Y. If those two things happen, then psi has to match A1 star B1, A1 star 1B with X star 2Y. So here again is what we would like to happen. Psi of A is, if psi of A is X and psi of B is Y, then psi of A star 1B should be X star 2Y. Well, we can condense this into a single equation if we replace this X by psi of A and this Y by psi of B. we get it condensed into a single equation. Psi of A star 1b has to be equal to psi of A star 2 psi of B. So this gives us the following definition of isomorphism. This is probably the easiest definition of isomorphism to use. There might be others, but here's a way of saying it precisely. We have two groups, G1 star 1 and G2 star 2. An isomorphism from the first group to the second is a one-to-one function psi from the first set G1 to the second set G2. I want to emphasize the word onto here, such that for all A and B in G1, psi of A star 1b is psi of A star 2 psi of B. So an isomorphism has to be one-to-one. It has to be on to G2, and this equation must hold for every pair of elements A and B in the group G1. So this is usually known as the isomorphism equation. If it's clear from the context which operations are intended, then we will simply say psi is an isomorphism from G1 to G2. Not so much on the slides or the videos, but in the book, the author is pretty consistent about not mentioning the operations. And then two groups are isomorphic if there's an isomorphism from the first group to the second one. And again, if it's clear from the context what the two operations are, then we will simply say that G1 is isomorphic to G2 without mentioning the operations. Okay, and here are the two groups we looked at in our first example. These are isomorphic groups. Here are the tables again. So how would we match the elements of Z3 with the elements of the group generated by the cycle 1, 2, 3? Well, we would match 0 with alpha to the 0, 1 with alpha to the first, 2 with alpha to the second. And so it looks like the function, the isomorphism, would be the function defined by f of n, where n is one of the numbers 0, 1, or 2. F of n is alpha to the n. This is an isomorphism, although at least for now we're not going to do any proof in this particular case. Although we will see several proofs later in the video. Okay, let's try this example. So 2z is going to be represent the set of even integers. I think we've used this notation before. So then the two groups, the integers using ordinary addition and the even integers using ordinary addition, are isomorphic. So when I'm claiming they're isomorphic, what I'm claiming is that there is a function, f, from z to 2z, a one-to-one function, which is on to 2z, for which the isomorphism equation is true. So what is a formula for an isomorphism, a function from z to 2z? Well, there is one obvious function from the integers to the even integers, the function defined by f of n equals 2n. This will take an integer input and give you an even integer output. We would have to prove that it's actually an isomorphism, but rather than do that, we're going to look at a second example where we will give the proof. So I phrase this as a question. Suppose instead of using the function f of n equals 2 times n, we use the function g from the integers to the even integers defined by g of n is equal to minus 2n. Is this also an isomorphism? Well, the answer is yes. I've just put the function up here at the top of this slide so we have it available for use. This is an isomorphism from the integers to the even integers, where in both cases we use ordinary addition as the operation. We are going to look at the proof on the next slide, but before we look at the proof, I just wanted to say a couple of things. The first being, what do we have to prove? We have to prove g is 1 to 1. We have to prove that g is onto the set of even integers. And we have to prove the isomorphism equation. We have to prove that for every pair of integers a and b, g of a star 1b is g of a star 2 g of b. And since in both cases the operation is ordinary addition, this equation that we have to argue for is actually g of a plus b is g of a plus g of b for all a and b in the set of integers. Okay, we are going to start by showing that g is 1 to 1. Here's the definition of 1 to 1. A function g from a set capital G1 to another set capital G2 is 1 to 1 if and only if for all a and b in G1, if g of a equals g of b, then a equals b. This is sort of an indirect way of saying that if you start with two different elements here in G1 and apply a little g to them, you have to get two different elements of G2. It's phrased this way because this is the easiest formulation to use when you are doing proofs. Okay, so we know what 1 to 1 means. It's a for all statement followed by an if then. So to show that g is 1 to 1, we are going to assume that we have an a and b in the set of integers. That's the G1 in our example. And we're going to assume the hypothesis of the if-then, namely that g of a equals g of b. And we have to prove the conclusion of the if-then. We have to prove a equals b. Okay, so the assumption that g of a equals g of b will give us, if we use the definition of g, gives us the equation minus 2a equals minus 2b. We are trying to argue that a equals b, which we do simply by dividing both sides of this equation by negative 2. We are done with the proof that little g is 1 to 1. To show that g is onto the set of even integers. Here's the definition of onto for a function little g from a set capital G1 to capital G2. Little g is on to capital G1 if and only if for every y in G1 there is some little x in, for every y in G2, there is some little x in G1 such that g of x equals y. For every element of the second set, there has to be something in the first set that g matches with the element in the second set. Well, this is also a for all statement, so to show that g is onto the set of even integers, we will assume that we have a y in the second set, which in our case is the set of even integers. And then we have to prove what follows the for all statement. We have to prove that there is some x in the set of integers which G matches with this even integer y. Well, the first thing to note is that because y is an even integer, we know there's some integer a for which y equals 2a. And now we are proving that there is some integer x in this, some integer x for which g of x equals y. In order to prove there is an object of a certain kind, you ordinarily have to construct that object out of the things you have available. And at this point in our proof, we have two things available. We have the even integer y, and we have the integer a for which y equals 2a. Somehow we have to construct an x out of those two things. I'm going to do a little scratch work here. Put the scratch work in the parentheses. This would not appear in a finished proof. So here's the scratch work. We're trying to construct an x for which g of x equals y. So g of x is minus 2x according to the definition of g, and y is 2a. So we want an x for which this equation is true. And it looks like solving for x by dividing both sides, the far left and the far right, by minus 2. X is minus a. This is the choice of x that ought to work. So, ending the scratch work and returning to the proof, we are going to let x equal minus a. And now we have to argue that this choice of x works. In other words, that g of x is y. So we simply start with the left-hand side of this equation, g of x. According to the definition of g, that's minus 2x. X is minus a. That's the x we constructed. Minus 2 times minus a is plus 2a, and that's y. We have finished the proof that little g is onto the set of even integers. And now finally we have to argue for the isomorphism property, which, as we noted before, is for all a and b in the set of integers, g of the quantity a plus b is g of a plus g of b. And the way we're going to do this is simply try to simplify both sides of this equation and see that they simplify to the same thing. So assume a and b are integers, then g of a plus b. According to the definition of little g, to get g of a plus b, you multiply a plus b by minus 2. Distributing the minus 2, we get minus 2a plus minus 2b. And now the other side of the equation, g of a plus g of b, g of a is minus 2a, g of b is minus 2b. We see that we did simplify, the two sides of the equation did simplify to the same expression, and therefore we know that g of a plus b is g of a plus g of b. Now I want to list a few properties of isomorphisms and isomorphic groups before we go on and look at more examples. First of all, if two groups are isomorphic, then the sets for the two groups have to have the same size, have to have the same number of elements. This is because an isomorphism is a one-to-one function from one set onto the other one. And that's what you need to have in order to know that two sets have the same size. Just a reminder that a set between these absolute value signs is shorthand for the number of elements in the set. If f is an isomorphism, then f of E1 has to be E2. E1 is the identity in the first group, E2 is the identity in the second group. And here's the reason for that. We calculate f of E1 by first replacing E1 by E1 star 1 E1. We know when you multiply the identity by itself in any group, you get the identity. And then we use the isomorphism equation. This is f of E1 star 2 f of E1. And now we multiply both sides of this equation by f of E1 inverse. If you multiply the left-hand side by f of E1 inverse, you get the identity in G2. And if you multiply the far right-hand side by f of E1 inverse, you're left with just f of E1. So E2 is f of E1. An isomorphism has to match up identities. F of the inverse of A is the inverse of f of A. And we're going to argue that the thing on the left-hand side is the inverse of f of A by multiplying f of A by the thing on the left-hand side. If we get the identity, then we will know that f of A inverse is the inverse of f of A. Using the isomorphism equation, this is equal to f of A star 1 A inverse. A star A inverse, A star 1 A inverse is the identity, and as we know from the previous bullet, f of the identity in the first group has to be the identity in the second group. And in general, f of a power of A, if you take an element little a of the group G1, raise it to a power, and then apply the isomorphism f to it, you will get the same thing you do when you apply the isomorphism f to A and raise the result to a power in the group G2. The proof would be by mathematical induction, and at least for now we are skipping the proof. F inverse will be an isomorphism from G2 to G1. This is another property of isomorphisms that is easy to prove, but for the time being we're not going to do the proof. If you have an element of G1, that's the little a here, and if you know you raise it to the nth power and you get the identity, then when you calculate f of A and raise it to the nth power in G2, you will get the identity of G2. This really follows from the first bulleted item here. If two groups, G1 star 1 and G2 star 2, are isomorphic, then the first group is commutative if and only if the second group is commutative. If two groups are isomorphic and the first group is cyclic and generated by the element little a, then the second group is cyclic and generated by the element f of little a, and vice versa. So, as a consequence, if you have two isomorphic groups, G1 star 1 and G2 star 2, then the first group is cyclic if and only if the second group is cyclic. And now here is a useful fact. This will come up in the problems that you will be doing. For any integer n, positive integer n, z sub n with the operation plus sub n is cyclic. Z sub n is the cyclic subgroup generated by the number 1. Okay, let's try a few examples. Here's an example of two non-isomorphic groups, u sub 5 and u sub 7. Why are they not isomorphic? U sub 5 has 4 elements, namely the numbers 1, 2, 3, and 4 has 4 elements, the numbers 1, 2, 3, and 4. And u sub 7 has 6 elements, the integers 1 through 6. In other words, the number of elements of u sub 5 is not equal to the number of elements of u sub 7. They would have to be equal if the two groups were isomorphic. Z sub 6 with the operation plus sub 6 and the symmetric group S sub 3 with composition are not isomorphic. So this is the group S sub 3 that we looked at earlier in the slides, the set of all permutations of the numbers 1, 2, and 3. They do have the same number of elements. S sub 3 has 3 factorial, or 6 elements, and Z sub 6 has 6 elements. But Z sub 6 plus sub 6 is commutative, and S sub 3 with the operation of composition is not commutative. Isomorphic groups, if you have two isomorphic groups, the first is commutative if and only if the second is. You cannot have a commutative group isomorphic to a non-commutative group. The groups u sub 5 times sub 5 and u sub 8 with the operation times sub 8 are not isomorphic. They do have the same number of elements. U sub 5 contains the integers 1, 2, 3, and 4, and u sub 8 contains the integers which are relatively prime to 8. In other words, the integers whose greatest common divisor with 8 is 1. Or in other words, the integers from 1 through 7 which are not divisible by 2. 1, 3, 5, and 7 is u sub 8. So the two groups have the same number of elements. We cannot claim they are not isomorphic based on having different numbers of elements. But u sub 5 is cyclic, and u sub 8 is not. How did I determine that u sub 5 was cyclic? Well, I calculated the cyclic subgroup of u sub 5 generated by 1, and then the cyclic subgroup generated by 2, and so on. And when I got to 2, I found that the cyclic subgroup generated by 2 is all of u sub 5. So u sub 5 is cyclic, and it is generated by its element, the number 2. U sub 8 I did in a similar way. I calculated the subgroup generated by each of its elements, 1, 3, 5, and 7, and in none of those 4 cases did I get all of u sub 8. The subgroup generated by 1 I really didn't have to check. That will consist of only the identity element 1. The subgroup generated by 3 had elements 1 and 3. The subgroup generated by 5 had elements 1 and 5. And the subgroup generated by 7 had elements 1 and 7. Since none of those are all of u sub 8 is not cyclic. And as we know, for two isomorphic groups, one is cyclic if and only if the other is. We cannot have a cyclic group isomorphic to a non-cyclic group. Okay, another example, which I have phrased as a question. We're now looking at the function from the integers to the integers defined by f of x equals 2x. Is this an isomorphism from the integers using the operation of addition to the same group? The answer is no. F is not onto the integers. Right? There were three requirements for being an isomorphism. An isomorphism has to be one-to-one, it has to be onto the second group, and it has to satisfy the isomorphism equation. But f is not onto the integers. In other words, not every element of the integers is f of x for some x in z. If you apply f of x, if you apply f to an integer x, you will always get an even integer as output. So the odd integers are not in the range of the function f. And as an example, 7 is not f of x for any integer x. Okay, moving on to another example. Here we are taking the function f from the real numbers to the real numbers, defined by f of x equals 5x. And this is an isomorphism from the real numbers using the operation plus to the real numbers using the operation plus, from the group R plus to itself. We are going to look at the proof on the next slide. Here's a case where I wanted to make a few remarks first. A definition: an isomorphism from a group G star to itself is called an automorphism of the group G. Just a little bit of terminology that we will use from time to time. Second observation: for any group G, comma star, there is always at least one automorphism of the group. In other words, there's always at least one isomorphism from the group to itself. The identity function, the function defined by f of x equals x, will always be an automorphism of a group, for any group. And the third remark that I wanted to make is that this example shows that there can be more than one automorphism of a given group. So for the group R plus, the identity function f of x equals x is an automorphism, and as we will show, so is the function f defined by this equation, an automorphism of the group R plus. Okay, so we have to show that f is one-to-one. We have to show that it is onto the real numbers. And we have to show that the isomorphism equation is true of the function f. So starting with the one-to-one property, we'll assume a and b are real numbers, and that f of a equals f of b. Using the formula, the definition of the function f, this means 5a equals 5b. So dividing both sides by 5, we get a equals b. This is exactly what we have to do to show that f is one-to-one. Assume f of a equals b, and show that a equals b. To show that f is onto R, we pick a y in R, assume y is a real number, and we have to construct a real number x for which f of x equals y. We have to construct x out of what we have available, and in this case what we have available is y. Well, after a little scratch work, I decided that x equals y over 5 is what's going to work. So we're letting x be y over 5, and now we will check that f of x equals y. F of x is 5x, according to the definition of the function f. X is y over 5. 5 times y over 5 is y. This completes the argument that f is onto the real numbers. And finally, we want to show that the isomorphism equation is true. Since the operation is ordinary addition for both groups, the two groups are identical, what we have to show is that for all real numbers a and b, f of a plus b is f of a plus f of b. And as before, we're going to argue for this equation by simplifying both sides and seeing that they simplify to the same thing. So the left-hand side is f of a plus b. According to the definition of f, that's 5 times the quantity a plus b, which is 5a plus 5b if you distribute the 5. And the right-hand side, f of a plus f of b, using the definition of f twice, is 5a plus 5b. And both sides have simplified to the same expression. The equation is true, and we are done. Okay, let's try this example. We are using the same function, same formula for the function. F of x is 5x. But now we are looking at the function from the positive reals to the positive reals, defined by f of x equals 5x. This is not an isomorphism from the positive reals with the operation of multiplication to the positive reals with the operation of multiplication. We can prove that f is 1 to 1 and on to the positive reals like we did in the previous example, but the isomorphism equation does not hold for this choice of f and these two groups. So the operation in both groups is multiplication. So the isomorphism equation in this case would be for all positive real numbers a and b, f of a times b is f of a times f of b. If we make an attempt to simplify both sides of the equation, the left-hand side, f of a times b, is according to the definition of f 5 times a times b. And the right-hand side, f of a times f of b, is 5a times 5b. This simplifies to 25ab, and in general 5ab and 25ab are not equal. An example would be if a is 1 and b equals 1. Okay, here are some useful facts about isomorphisms. This is a summary of things we have discussed in this video. So, assuming that f is an isomorphism from the group G1 star 1 to the group G2 star 2, then, as we know, G1 and G2 have to have the same number of elements. F of the identity in G1 has to be the identity in G2. F of A inverse has to be equal to F of A inverse. So this inverse is taken in G1. When you apply F to A, you get an element of G2, so this inverse takes place in G2. In general, F of A to the n will be F of A quantity raised to the n. F inverse will be an isomorphism from G2 to G1. If A has order n in G1, then f of A has order n in G2. So you remember that the order of an element, A, is the smallest positive integer n for which a to the n is the identity. G1 is commutative if and only if G2 is commutative. G1 is the cyclic subgroup generated by A if and only if G2 is the cyclic subgroup generated by f of A. And it follows that the group G1 star 1 is cyclic if and only if G2 star 2 is cyclic.